Hi everyone, my name is Neha Kadam and today we are going to study printed circuit board. This is a ELEC 239 class and we will start with our first lecture. In this lecture, we will study fundamentals of printed circuit boards. As you can see here, this is the short form of PCB, commonly used in electrical industry. And then we will discuss different materials used in PCB designing. And later we'll learn about the manufacturing process and then steps to design a PCB. Let's begin with printed circuit boards fundamentals. Now, what is a printed circuit board? So, printed circuit board, it is essentially a board which provides a mechanical structure and electrical connectivity to electronic assemblies by using conductive tracks, pads, and other features. PCB is also a basic building block of any electronic design and has developed over the years into a very sophisticated component. The picture on the left hand side you see is the wire wrapping before the PCB was invented. You can see here how complex these wirings are when there were no PCBs there. So here you can see the type of circuits uh, at that time were constructed through a laborious process of point-to-point wiring. As the wire insulation began to age and crack, this type of circuit interconnection had frequent failures at wire junctions and short circuits. Whereas on the right side, when you see this picture, this shows the PCB. This is one of the PCB circuit, and this might have come up after the invention of the PCB. So this circuit shows like with the advancement in the electronics field, thus as you know that as you can see here, the components, the size and the cost of these electronics components began to decrease. Electronics became more prevalent in consumers' goods, and the pressure to reduce the size and manufacturing cost of electronic products basically drove manufacturers to look for a better solutions. And that's how these PCBs were born. And you can see here on the picture how neat and clean this circuit is compared to the wiring one. Um, and here the conductive path is shortest compared to the circuit you see on the left hand side. Now we'll move on to the next slide. Now the question comes, why to use the PCB? It's easy mechanical assembly of the electronics components. Actually, in the PCB, the designing part is done by the PCB designer, and at the end, when you receive the end product, uh, after the designing of the PCB, the assembler basically puts up the component on the PCB designing, which is very easy for assembler to put it on the PCB board when compared to the wiring system which we saw in the previous slide. And the other reason it provides a reliable electrical connection, yes, because we can have the shortest path between two components, and which is difficult to achieve in a normal wiring connection. And also we can avoid situation like short circuit, and we can also have multiple ground planes and multiple power supplies. Third point is often used for thermal control for components. So this is a really good feature of a PCB. thermal reliefs are provided on the PCBs to avoid any kind of heat, and it is very useful for PCB to survive for a long duration of time. And other than that, PCB also allows signals and power to be routed between physical device, and solder is the metal that makes the electrical connections between the surface of the PCB and the electronic components. And being metal, solder also serves as a strong mechanical adhesive. So that's why PCBs are used more commonly nowadays. Now moving on to the next slide, which is disadvantages of using a PCB. The first it mentions is the tooling cost, requires more investment to support the design of a PCB. Uh, Definitely, the cost of making the PCB is a lot because you have to go through different process. Like you need to hire the PCB designer, and then once the design is complete, then it goes through a different process, like either milling or the etching process, which are expensive, and that too if you're doing it for a bulk PCBs. Designer costs. This is where you make the big bucks as a designer. It requires special skills to design a PCB well. So yes, there are several softwares available to make the PCB. For example, Eagle, KiCad, Mentor Graphics, Altium, Fritzing, etc. And the PCB designer, they are perfect in designing the PCBs using some of these software, or they work on any particular maybe software, and they make a really good money out of it. So the cost of the designer is also involved in designing the PCB, and uh, uh, as a designer, it is good because you will earn a lot of money, but it is a disadvantage for a if we include it as a cost. Next is time. The time it takes to make the PCB is a lot. So if we count from the beginning to the end, like first capturing the schematic and then going through the design process from the software point of view, and then uh, sending it to the companies, or doing it by yourself using the milling process or chemical etching process. All in all, it takes a lot of time to do that. So these are some of the disadvantages, and there are a couple of other disadvantages, like the copper tracks in the PCB are very thin. They can able to carry less current, hence a PCB cannot be used for heavy currents, because in that case the strips will be heated up and cause problems. And if we compare with the breadboard, in breadboard you can change the connections to test out different scenarios, whereas this is very difficult in PCB, because once the design is complete, no change can be done into that. Now moving on to the next slide. Here comes the different materials used in making the PCBs. So here it's written, PCBs are composed of a sandwich of layers called a layer stack, and consist of substrate layer, conductor layers, and other physical layers and manufacturing layers. So substrate layer is basically the insulation layer, uh, in which there is no uh, electrical connection is made on that layer, and the substrate layer is basically made up of fiber or glass or epoxy, and and in the PCB, you can have multiple layers of PCBs, starting from the single layer PCB, which has just the substrate, and on the top it has a copper foil layer. And second one is double layer PCBs. It has substrate in the middle, and on the top and at the bottom it has copper layer. And then if you go further, there are multi-layer PCBs which has multiple substrate in between the copper layers, and it can go up to 32 layers of PCBs. So you can imagine how many multiple layers we can have in the PCB, and uh, how we can have uh, interconnection between all those layers, how complex that would be, thinking about if we have like 32 layers PCB. This conductor layer is used to provide the electrical connection between any 2 points. And in the PCB, you have multiple conductor layers in order to provide the electrical connections. Next comes the other physical layers like silkscreen markings, solder masking, adhesive layers. If you see the silkscreen markings, they are basically used on the component side to identify the components, their test points, parts number of components, warning symbols, or company logos, or manufacturer marks, etc. These silkscreen requires specially formulated inks, standard colors, for example, black, white, and yellow. Solder mask is basically provides a thin layer of polymer. It is used to provide protection against oxidation and to prevent solder bridges from forming between closely spaced solder pads. And then this adhesive layer is basically used to provide bonding between the substrate film and the copper conductor. Um, in some cases, especially double-sided flexible PCB design, the bonding area also can be adhesiveless. Manufacturing layers. These layers are basically they are the drills and the places where uh, the drill is placed so that you can get a perfect design. That is called your manufacturing layer, so that you have the perfect mechanical assembly on the PCB. Now, going to the next slide, we have this manufacturing method here on the slide. You can see two pictures. First shows the PCB from a milled method, and second from a chemically etched method. So these are the mainly two methods are used to design the PCB. These are called manufacturing methods. First, we'll see this milled PCB, minimum material removed to cut trace out of top copper. Top copper remains in the spaces between traces substrate. Wait, has been disturbed. And then second one is chemically etched PCB. Most of material removed and substrate smooth and uniform in this case. So these are the two different methods, and two different processes are involved in making the PCB. In the milling milled PCB, there is a CNC machine we have in our lab which we use uh, to to get the holes on the PCB design. So this whole design is created on that machine. Whereas in the chemically etched process, there are um, uh, different steps involved in making the PCB in chemically etched process, and we will go through that in our next coming slides. So milled versus etched cross section. So this picture basically shows like how in the milled uh, PCB designed by the milling process, how it has notches, like here you can see. Whereas if you go for a etching process, then it will cause slight rounding in trace material. However, there will be no damage to the substrate. PCBs are all made of layers, but how those layers are created vary. Typically, two methods are most common. So these are the same thing, chemical etch and mechanical etch. The conventional etched process is explained, and in this process, there are different steps involved in creating the PCB. So I'll explain each step. Uh, First, you make the PCB design using any PCB design software like Eagle, Graphics, KiCad, FitSync, etc. And once you have the design, you take the printout of that design on a shiny side of the transfer paper. And then next, what you will do is sand the copper plate so that there is a rough surface for the design to stick to when transfer. And then you wash the copper plate with some water and rubbing alcohol and let it dry for a few minutes. And then you cut out the design and place them face down on the copper. And then you run the copper plate with the design face down through a laminator. It will take around like 5 to 7 times until the plate is hot. And after running plate through laminator or iron, the ironing the plate, you will basically put the plate into a cold bath and then agitate until the paper floats off. And then place the PCB into the etching solution and agitate for 25 to 30 minutes or until all the copper has dissolved around the design. And once all the copper is gone, rinse it in the water bath and let it dry and use rubbing alcohol to wipe off any ink transferred onto the PCB. Now you have a etched PCB, but you still need to drill the holes. So here you can see you will drill the holes and then the conductive layer is plated, including the holes. And then here you can see the solder mask has been applied. And this is the silk screen, which is basically used for labeling. It has been placed here, has been put here actually. Now going on to the next slide. So here I have put a video of chemical etching process and I would like you all to see it. It's it's a short video and I hope you'll enjoy it.
When I first got into electronics, I was really put off by the idea of etching my own circuit board. It seemed like a lot of trouble, hassle. I'd been using breadboards, like this one. They were just really temporary and fragile. And perf board is definitely more sturdy, but I found the layout process to be kind of confusing, and it led to a lot of mistakes. So finally, out of frustration, I did try etching, and I loved it. I could lay out a circuit any way I wanted and draw clear and visible connections between the parts. Now, there's a lot of different ways you can do this. The method I've found to be most effective is the photoresist. Let me show you. I'll start with a design. There's a ton of PCB layouts available on the web, and most of them can even be built without knowing how they work first. Here's an audio synthesizer design that I made using the CADsoft Eagle program. The first step in turning it into a real board is printing it out. I've found these overhead projection transparency sheets to work pretty well for this. But I'm still not too impressed by the output of my laser printer. Might be time for a new toner cartridge. Any gaps in the ink can lead to tiny holes in my copper traces, which is not good. But that's why I always print out and cut 2 copies. By doubling them up, I usually block out any gaps. And I can always cover any remaining with a bit of precision Sharpie work. You can buy specialized exposure frames, but a cheap photo frame really works quite well for keeping the transparency pressed against the board. The shiny or unprinted side should face the glass, so that the ink can be as close as it can to the actual board. A small piece of tape will keep it from slipping around. I picked up the etchant, developer, and light-sensitive board I'll be using from Jameco's website. The pre-sensitized boards come with an opaque white film on them to avoid accidental exposure to ultraviolet light. In the past, I have opened them up in dimly lit rooms without causing any harm, but to be safe, you can use a red light source. Luckily, I happen to have a few red LEDs around. Peel off the protective film, making sure you don't get any dust or scratches on the board surface.
So this was the video about chemical etching process and how nicely this guy has showed each steps involved in making the PCB using the chemical etching. Now we'll go to the next slide, and in this slide you will learn about the mechanical etching, and in this video it will show how the PCBs are milled using the CNC machine. So I'm going to play this video.
To 10 parts water in a Pyrex dish. These dishes are nice because I can even heat them if I need to, and they come with a lid so I don't have to remove the developer in order to store it. Once my 8 minutes are up, it is development time. When working with developer or etchant, I wear these nitrile gloves I picked up at the local pharmacy. They're very purple. Fully developing the board usually takes around a minute or so. Agitating or rocking the dish back and forth keeps fresh amounts of chemical flowing over the board and removes the unwanted resist coating that's flowing off. Once all of the exposed areas are all bright and shiny, totally free of resist, we can pull the board out and give it a quick rinse in cold water. At this point, you could scrape away any unwanted resist or fill in any holes that you spot with a fine point permanent marker. If everything looks good, then it's time to move on to the etching. There's a number of chemicals you can use for etching, but the most popular is probably ferric chloride. I'm using a mixture of 1 part concentrated ferric chloride to 1 part water. Now be careful, as this stuff will stain almost anything and easily mess up any metal surface. You'll definitely want to avoid skin contact and keep a well-ventilated work area. The entire etching process takes around 20 minutes. When I first put the board in, I'll agitate for about 30 seconds to a minute. Then I'll leave it alone, come back every few minutes to check on it, and agitate a bit more. This one's almost done, but still has some areas in the middle that need a bit more time. Once I'm sure all the exposed copper has been removed, I give the board another quick rinse and another close-up inspection. Looks good, so we're ready to drill. I'll use this mini drill press stand along with a 0.8mm bit for the component holes and around a 1.5mm bit for the wire pads. It's important to use eye protection and a dust mask while drilling. I also keep a vacuum hose close by to remove the excess bits that tend to pile up while I'm working. When I'm pretty sure I'm done, a careful look around the board usually turns up at least one hole that I've missed. Yep, there it is.
So you saw the milling process in the last video, and you saw how the guy created 3 different designs from the CNC machine, and how easy it was to make that, and it didn't consume much time to use that process. And so now here is the question: why do you think it is important to know how your PCB is going to be made? I want you to think about this question and answer it to me by doing some research. And for that, you'll get 15 minutes to do the research, and then we will come back to the lecture. Your time starts now. All right, you might have come up with some answers for this problem. We will discuss the solutions later on after we finish this lecture. Now I'll go to the next slide. Steps to design a PCB. So in our program, we'll be using KiCad software to design a PCB, and in this, using the KiCad software, there are different steps involved in creating the PCB, and we are going to study those steps. So the first is the schematic entry, and under that we have a selection of the components, connect to create schematic, electrical design rule check, netlist creation. uh, all these four steps comes under schematic entry. Now, what is schematic entry? It is basically a multi-step process in which a software tool called a schematic editor is used to build a netlist. So schematic editor is, so this basically you will see on the top of your screen when you use the KiCad software. And if you click on that, you can select the component and start building up the schematic. Um, and here it says it's used to build a netlist. Netlist is basically a simple text file, and you can inspect it with a text editor. When you open that file, you will notice that the file contains all the information about the PCB layout program, and it will need and you will need it in order to know which components are supposed to be included and what are the connections between those components, and their information about the nets, and so on. Next, we will next steps into this process is the PCB layout process, and which require import of the netlist and then placing of the actual placing of the components, and then root traces, PCB design rule check, and generating the CAM files. So here, in this PCB layout step, you will see that these are the following steps which will be used, and in total we have uh, 9 steps. Select the component, connect to the create schematic, design rule check, create netlist, and then import the netlist, place components, route traces, PCB design rule check, and then generate the CAM file. Now we are going to see each of them individually. So first is the selecting the component. So when you open up the KiCad software, to select a component, you have to go to the library. Library is basically a file that contains all the components you will need to design your schematic circuit. In some cases, the library is shared by both the schematic capture program and the PCB layout program. Some of the libraries are shared, meaning that they contained not only information about the schematic representation of the circuit, but electrical characteristics and mechanical information. Some software packages use separate libraries also, depending upon the complexity of the software itself. So with KiCad, it's usually pretty easy. Next step is connect to create the schematic. So schematic will vary depending upon what design you are using. So according to that, once you have selected the component, you will start interconnecting those component based on your circuit. And then next, you will do the electrical design rule check. Now, what is electrical design rule check? It's basically involves checking a design for a proper contacts and spacings. It ensures correct power and ground connections. Electrical rule check um, also a step which can involve checks for unconnected inputs or shorted outputs. It also checks the robustness of a design, both at a schematic and layout levels, against various electronic design rules. And next is create netlist for export to PCB program. So once you have done the rule check, then the netlist will be created. This you will learn when you do the tutorial. You will get to know how the netlist is created. And so let's assume we have the netlist and you have created it. Next is the PCB layout. Once the schematic is created, net is listed. The netlist files are opened in the PCB layout program, and the PCB is designed. So you import the netlist and then you place the components. So here placing the components means you place the actual, uh, you know, actual figures of the components on the PCB layout design. And so this says the layout program will take the netlist and load the appropriate footprints and create a red nest. Red nest is basically the internet connection between the components. So if you're using multiple pin connection circuit boards, then its red nest may look very complex. And you create the PCB following the electrical connection of the schematic. Now we'll go to the next is placing of the components. So the placing of the component, it is often done by human visualization on the schematic. The schematic sometimes has no bearing on the component of the no bearing on the placement of the components on the PCB. However, good schematic entry will help in troubleshooting the end products, and it will also help in the placement of test points both on the schematic and the PCB, and it will aid in troubleshooting. It's not necessarily that the job of the PCB designer to figure out where these should be, but a good designer will make sure to ask if they see any necessary or include any that are made available. Now next is the route traces. Once the footprints are placed, the traces are laid out to connect them electrically. Planes are also designed at this step. So this is a quite easy step once you start using the KiCad software, you'll get to know how easily you can do the routing trace. You can make the routing traces. Now next comes the design rule check, and PCB design rule check is very important. It is the area of electronic design automation that determines whether the physical layout of a particular chip layout satisfies a series of recommended parameters called design rules. Design rule checking is a major step during physical verification sign off on the design. And it also involves layout versus schematic check, electrical rule check, and if you have any antennas in the design, then checking of that. It is particularly recommended that a batch mode design rule check always be performed prior to generating the CAM files. Now, CAM files are the last step. Once you generate the CAM files, uh, generate the CAM files, then you can basically print. You will use that CAM files if you are using the milling method. You can print those CAM files and not exactly print. You can use it in the CNC machine and you can mill your PCB. And if you're using the etching process, then you can take the printout of those CAM files. Uh, the standard format which is used for CAM files are Gerber 274, and we might be using Gerber files in KiCad. And to read about the PCB design rule, you can refer to the reference slide at the back of this PPT. Now is the classroom activity. You will need to come up with a three device data sheet from your previous or the current projects. You will need to find the footprint information and bring that to class. So you will have like 30 to, you can use like 1 hour to work on this activity and then come up with the result. So these are the references. You can go through the references. That's it. Thank you.